Alright, so we're going to go ahead and continue our discussion and start talking about kinetic energy. And kinetic energy is the energy of motion. So we describe it as follows. Kinetic energy, K, is equal to 1/2 the mass times the velocity of the object squared. Okay? And if we have multiple velocities, we'll have the summation over the mass times velocity squared. Okay, so this is our kinetic energy, and we can express this in terms of momentum as well. Remember that momentum is equal to mass times velocity. Okay, so we can use this form here and substitute it into our kinetic energy equation up here. Substitute our velocity in, so velocity from here would equal momentum over mass. Okay, so we would plug that in right there and then find our kinetic energy is equal to momentum squared divided by 2 times the mass of the object. Okay, and so we'll look at a few examples how to use this here in a bit. The SI units of it, since it is an energy, it is going to be in joules as well. Okay, so we can make sure that this makes sense, since remember a joule is also a Newton meter. Remember that newtons is kilograms meters per second squared. Okay, so this is the breakdown of a joule. And we can look back at our kinetic energy equation and say, okay, we have mass, which is in kilograms, and we have velocity squared, which would mean meters per second, the whole thing squared. So we have meters times meters, which is squared, which would be meters squared, divided by seconds squared. So this does make sense. Okay, so let's go ahead and look at our first example, 7.7. A 75 kilogram person walks down the central aisle of a subway car at a speed of 1.5 meters per second relative to the car, whereas the train is moving at 15 meters per second relative to the tracks. Okay, so now we are combining our little bit of information we have learned about relativity with our knowledge of kinetic energy. Okay, so the first part is, what is the person's kinetic energy relative to the car? Okay, so remember that kinetic energy, I'm going to write it up here, is equal to 1/2 mv squared. Okay, so our kinetic energy here will be 1/2 times the mass of the person, which is 75 kilograms, times our velocity of the person relative to the car. So that is going to be the velocity here relative to the car, which is 1.5 meters per second. Okay, now notice one thing. It says that this person's speed relative to the car. Okay, remember that speed is scalar. So no direction given. Okay, so this means that the person relative to the car might be positive or might be negative. We don't know, so we're just looking at this as a scalar quantity. Okay, and we do know also that kinetic energy is scalar as well. I should have written that here. Scalar. Okay, just like work was. Okay, so we can find our kinetic energy of the person relative to the car. So 1/2 times 75 times 1.5 squared. And we get that the kinetic energy is 84 0.4 kilograms meters squared per second squared, or remember this is joules. Okay? Alright, so part B states what is the person's kinetic energy relative to the tracks. Okay, so in the last one we were looking at relative to the car. Now we're looking at relative to the tracks. So we have to take now both of these things into account. The speed of the person relative to the car and the train moving and its speed relative to the tracks. Okay, so when we talked about a little bit about relativity, okay, we had this equation. So we have the velocity of the person relative to the track, so that's how I'll label it. And we know it's going to be equal to the velocity of the person relative to the car plus the velocity of the car relative to the tracks. Okay, and we do have both of these quantities given in our problem. Okay, we just worked with that first one here. So, one thing to note is that we don't know the direction of these velocities. Okay, so our velocity here may be different. Okay, so we just have to kind of keep that in mind. So our kinetic energy then of the person relative to the tracks will be 1/2 times our mass, which is going to be the person's mass still, 75 kilograms, times our total velocity, which would be this here. Okay, so this would be 1.5 meters per second plus 15 meters per second, and that whole thing squared. And again, we don't know the direction, so in this diagram you can see he's either going in the positive direction or the negative direction, so either towards the front of, we can say that this is positive x direction, so he could either be walking in the positive x direction or the negative x direction. Okay, and we don't know which, so that kind of throws a little bit of a wrench in the problem. So this could be a plus or a minus right there. Okay. Okay, so let's go ahead and continue this on our next page. So K sub PT is equal to 1/2 75 kilograms. And then I'm going to reorder it so it looks a little nicer. It'll be 15 meters per second plus or minus 1.5 meters per second squared. Right? Right. Okay. So now we will have two little bit of different answers. So we'll have 0.5 times 75 times 15 plus 1.5 squared. Okay. So that answer would give us 10,000, about 200 joules, or 15 minus 1.5, and that will give us 6,830 joules. So these are drastically different kinetic energies. Okay, it's off about 4,000 joules. Okay, so just note that you want to cover all bases. If it doesn't state the direction of motion, then you'll want to make sure to add that in. Okay, that there might be two different possibilities. Okay? All right, let's go back to the problem. And the next one states, what is the person's kinetic energy relative to a frame moving with the person? Okay. So we have the person, okay, and they're moving with some velocity. And we have a frame of reference. Okay, we're going to say that's x. And it is also moving, I'm going to say v sub f, with some velocity. And it is moving with the person. So this frame of reference is actually like, let's say, on top of his head. Okay, it's just on the person. So they are moving together, meaning the velocity of the person is equal to the velocity of the frame of reference. Okay? So the kinetic energy relative to one another would then be, let's see, it's then going to be 1/2 mv squared, where v is the relative velocity, which relative to one another, since they are moving at the same speed and the same velocity, this velocity will be 0. Okay, so let me kind of write that in words. So velocity relative to one another is 0, since the frame of reference moves with the person. Okay, and so that is why the velocity here is 0. So that means that the kinetic energy of that situation is 0. Whoops, 0 joules. Okay? Alright, I know that was kind of a lot, but I thought that that was a good example to look at both relativity and kinetic energy. Alright, so we're going to go ahead and now talk about the work energy theorem. And to first talk about that, we want to go back and look at net work, which is the work done by all the forces that are acting on some particle or some object. Okay, so we are going to go ahead and define the net work as the change in net work is equal to F net dotted into our displacement vector here. Okay, remember that force is equal to mass times acceleration. Okay, so we can plug that in here. Okay, and then we can also remember that acceleration is equal to the derivative of velocity with respect to t. So again, plugging that in. Okay, and we can move around our dt here due to one of the properties of derivatives. I can't remember it off the top of my head, but we can move this around, so I can go ahead and move it to under the dr here, or the displacement. So now we have dr dt, and dr dt is the derivative of velocity, right? So now we have, or I'm sorry, it's velocity. Whoops, I meant to say velocity. Eraser. Okay, so dr dt is velocity. Okay. So now again, by I believe cumulative properties, we can switch those around, and now we get this final form here, mv dot dv. Okay. Now, if we take the derivative of this, and we can, or I'm sorry, the integral of this form, we'll get that the net work from a to b is equal to the integral from a to b of each component here. So this will be m v sub x dvx and so forth, and I'll continue this discussion on our next video.